Alright, so in this video we'll be starting our drivetrain gearbox. So if you remember in the first video, we covered how gearboxes work, what motors are, where they are, what kind of motors there are, how gears work, and how it all comes together into a gearbox, as well as using this JVN calculator over here to configure the gears that you will use, and etc. So today we'll be starting with the gearbox. And so the first part when you're making a gearbox is making this first plate over here. And so as you can see, where the motors go, where the gears go, all of that is decided by this motor, by this plate here over here. And this is where everything will be attached to. And so this is essentially the first and very most important part of a gearbox. And so that's what we'll be making. So we'll start with the new part. We're here, and I have a setting which automatically starts a sketch, but for demonstration purposes I'll just start a new sketch. We can start on the XY plane, and so here we are with a new sketch, and we want to create a gearbox. So first step is getting the JVN calculations done, right? So let's say we'll use Falcon 500s, 2 gearboxes in a drivetrain, 2 motors per gearbox, 154 pound weight, and let's say we'll use 4-inch wheels this time, and let's figure out what gears we can use. Now if you want to know what gears are available, what you can do is hop onto VexPro hex gears, just search that on Google, and you'll see multiple links here. You want to use the 20 dp 1/2 inch hex bore gears. What the 1/2 means is basically the inside of the gears has a 1/2 inch hex cutout, and so we can use a 1/2 inch hex shaft through them. And so if you scroll down, you can see all the possible sizes there are. So it starts with 18 and it works in increments of 2, so you have 18, 20, 22, 24, 26, and it keeps on going until you get to 84 teeth, and that's the biggest gear that they sell. And so those are all the possible gears we can use. So that's the gears over here, so 46, 20, 42. Now this gear over here, the small gear that attaches to the motor, those ones are not on this link over here. For that you have to search Falcon motor gears, Falcon 500, right? So we'll search that, and you can, if you scroll down to the VexPro link, you should be able to find, so this is the Falcon 500 motor page, and we should be able to find the gears here. Scroll down to all the ads here, click on accessories, and here we go, these motor pinions. So we could have searched for motor pinions, but if we click on there, so if you guys see here, it says 20 dp, and over here on these other gears that we use on our hex shafts, it also says 20 dp. So dp is it stands for diametral pitch, and basically what it means is it defines how these teeth are, how they're made, and basically if you have 2 gears that are both the same diametral pitch, they will be able to work together with each other. And there are also 32 dp gears that are used in FRC, but most commonly you see 20 dp. And the difference there is basically the 20 dp gears, they tend to be bigger, and so they'll take up a little bit more space, but they also are able to handle a higher load, and that's why you'll see them on drivetrains. So here we go to our motor pinions, and if you scroll down, you can see there's all sorts of options for different motors. So we have 8 teeth gears for Falcon, for the Falcon motor, right? And then we have 9, 2, 10, 11, 12, 13, and 14. And then there's a different set of pinions for the sim motors, and the sim gears also work with the neo motors. So for the sim motors, you have a smaller list of options. You have everything from 9 up to 14 teeth. And then there's pinions for other motors. So for example, the 775 Pro motor, you can also attach pinions to it, but we generally use it with a versaplanetary, right? So you have all these gears that can be used. So we can pick here anything from 9 to 14 because we're using the Falcon 500, actually 8 to 14. So let's say we go with 10, so we can change this around. And then the driven gear, right now we're at 11 feet per second, so that's a little bit slow. And our current draw is 61. So this is a very safe number, but we can go a little bit faster. So maybe let's try 44 teeth. So that looks better, a little bit better. We have 12 feet per second, and we have 64 amps in current. Let's see if we can go a little bit faster even. So let's try 40 teeth. So if you reduce these big gears over here, if you reduce their size, you'll get more speed, but less power. If you increase their size, you'll get less speed and more power. The contrary is true over here. The smaller your driving gear, the more power you'll have. The bigger these are, the higher the speed, but then the lower the power. So you can play around with this when you're deciding your gearbox. Maybe we can try a bigger gear here. So that's the 73 amps there is a little bit too much. So what we could do is we can change this 10 here to a 9 tooth. And now I like these numbers far better because 12.5 feet per second, so it's a decent speed, and our current draw is about 66 amps. So we're not going too fast, and we also have enough power. So what we can do is just go with these gears here. So we'll use a 9 tooth on the motor, similar to this gearbox, and then we'll have a 44 tooth gear connecting to it, and then a 22, and then a 40. So when we make our sketch here, the first thing we want to do is make these 9 tooth gears. So what we'll do is we'll make 2 circles. So we'll make a circle here, and we'll make another circle over here. Right, so we have our 2 circles here, and then the next gear in the middle is this 44 tooth. So we'll make a 3rd circle in the middle. That will be the 44 tooth. So these circles here basically represent the gears. Now, what we want to know is how far apart should these circles be from each other so that my gears connect with each other, right? So for that, what we need to get is the pitch diameter of these gears. So if you look closely, these gears mesh with each other, right? As you can see, let me remove this plate here. If you look carefully, you'll see that the gears actually they intertwine with each other, right? The teeth of this gear go a little bit inside of this space over here, and so I can't just use the outside diameter of these gears because then they won't mesh with each other. So to find the diameter at which they will mesh, what we do is we can head over here and scroll down on this Wex page, and if you click on drawing, you'll see this PDF kind of file here, and if you zoom in over here, you will see that here's the drawing of those gears. So the outer diameter is of the gear, and there's a pitch diameter. And so when any 2 gears, if their pitch diameters are touching each other, what it means is that they will mesh with each other. So if I were to make these 2 circles the pitch diameter of my 2 gears, and if I were to connect them, that would mean if I place my gears on them, they will mesh with each other, right? So we have a 44 tooth. Yes, we have a 44 tooth here. So if you look here, pitch diameter is this column here. So if we scroll down, 44 tooth, 2.2. So this is in inches. So 2.2 inches is our pitch diameter. So if you go back to our circle, we can add a dimension for 2.2 inches, right? And now we want the pitch diameter for this small gear here. So we're using a 9 tooth, and it's a motor pinion, so we have to go on the second website with the motor pinion, and we'll scroll down again, click on drawing, and you can zoom in, and this page is slightly different, but it gives you the tooth count. So we're using a 9 tooth here, so we have to scroll down, and this is the 9 tooth page, and we're looking for a falcon gear, and so our pitch diameter over here is 0.5 inches. So we'll use that over here. So we'll make this 0.5 inches. And now what this means is if I connect these 2 circles right next to each other, and if I were to place my 2 gears over here, they will mesh with each other perfectly. And that's what we want. So what I'll do to place them next to each other perfectly is we'll use tangent. What you can do is do tangent this circle and the second circle, and these two gears and these two circles are now connected to each other no matter where they go. And this distance between them, if we measure this distance here, 1.35, that's the exact distance we need for these two gears to work with each other. And so that's how you can use the pitch diameters, right? And so we have the same thing on this side, so we'll make the smaller circle equal to it, and we also need to make a tangent. So there we go. And then what we can do is have all these gears on the same level, so we can make them horizontally constrained. So the center of this circle should be on the same level as this circle, and the same thing here. And we want this to be symmetric to our origin point. So what we can do is just coincident the middle of this circle to the middle point. And there they are. So now they can't move, it's fully constrained. And so that's my first set of gears. My small gear, big gear over here. Just like how it is in the full CAD over here, right? Alright, let's move on to our next set of gears. So now we have a 22 tooth gear. Now remember, this 9 tooth gear here is special because it has to go on the motor. The other 3 gears are all of this hex kind, right? Because if you look in our CAD again, these small gears are the only ones that attach to the motor, and the rest of them are on hex shafts. So now I don't need this motor pinion page and I can close it. And we just need these sizes over here. So we're going for a 22 tooth and a 40 tooth gear. So we go back in our sketch, and we're going to make 2 circles again. So starting from here, this is our small gear, and we'll have a bigger gear over here, right there. And let's give them some sizes. So if we go back, we're looking for 22 teeth, and so if we scroll down, 22 teeth, right? And there's 2 of them because there's the aluminum and there's a steel version. Basically, for smaller gears like 18 tooth and anything below that, you want to try to use steel gears because the gears are smaller, they can't take as much load, and aluminum is weaker than steel. So for an 18 tooth, for example, we would generally use steel, but their sizes are the exact same. So we can use the pitch diameter of 1.1. So we go here, dimension 1.1 inches, and then let's go back, and our second gear, our final gear here is 40 tooth gear. So we'll scroll down to 40, and it's 2 inches in pitch diameter. So we'll go back and we'll make this 2 inches. There we go. And so the final step here is to make these 2 tangent, just like we did with the first set of gears. And right now the only problem is this gear can move around side to side. So we'll add a vertical constraint to it so that it remains in our origin point. And so this right here is a layout of all the gears and how they will mesh with each other, and this will work. And so this is the first part of making a gearbox plate. Now what we can do is make all these construction, and the reason why we need to do that is because even though these are the sizes of the gears, we don't actually need to extrude all these geometries here. What we need to extrude are like bearing holes and things. So the next part of this sketch would be to model in our motors, because if you look at this first plate over here, it goes around the motors. So we need to know how big our motors are, right? So we'll go in here, we'll make a circle over here and another one over here, and because the 2 motors are the same, we'll make them equal. Right, now we need to know the size. So what we can do is go here on our Falcon motor, or you could open it from the parts library. So if you go open, library, motion, motors, Falcon 500. If you open this file, let it open, and if you go under tools, there is a measuring tool. So what we can do is click on measure, and then you can select like this outer circular portion of the motor, and it will tell you, like in this case it tells us the area. If we select just the arc, it will tell us the diameter of the motor. So here it tells us it's about 2.4 inches, right? So what we can do is we can go in our sketch and we can add a dimension for 2.4 inches. So if you look here, these motors are close to each other. If you look in the assembly, they're also pretty close to each other, right? So this is where making this sketch is really useful, because if my gears were super small, my motors would be colliding with each other, which is not something you want, because that's not possible, right? You can't have these two motors going inside each other. So this is another place where making this sketch is really useful. Right, so the next thing that we need over here. Now, all these hex shafts need bearings on them, right? Because otherwise, how will they spin? So we need to make bearing holes. So what we'll do is take a circle and make two circles. So one circle here, one over here. We'll make them equal to each other because they're both bearings, and we'll give it a dimension. So bearing holes again are 1.125 inches. And if you want, what you could do is open a bearing file. So we'll go open and head over to bearings, hex bearing, open it, and again we can do tools, measure, and as you can see it's 1.125. It's close enough. So that's the number we'll use for the bearing holes. Right, so we have that. Now if you look here again on the gearbox, this plate and the gear actually goes a little bit inside the plate, right? So we need to have some clearance. We want to make sure that this gear doesn't run into our plate over here. And so if we go back here, remember the outer diameter is the outside of the gear. And so actually we'll need our motor page again. So motor, 20 dp motor pinions, there we go. Oh, what? Okay. All right, it says the page is outdated. Motor pinions. There we go, okay. Now we're on the right page. We'll go to drawings. There we go. And if we scroll down to the 9-tooth gear, as you can see, the outer diameter here is 0.602. So as long as this hole over here is bigger than 0.602, this gear can spin in here freely. So what we usually like to do is just make it a little bit bigger so that we can be rest assured that there won't be any problems. The gear won't jam against the aluminum plate. And so what we can do here is make this something like 0.775. And so we have those holes there. And this is starting to look like a gearbox plate, right? So the final component we're missing here, if you look, the motors have holes on them. So if I pull this Falcon out, if you can see, there's all these circles here, right? These are holes, and the reason for them is so that we can mount the motor, because if I were just to put the motor here, it'll slip out and fall away. And so the way we attach it is using these two screws over here, as you can see. These two screws, they're 10/32, or why are they quarter 20s? They should be 10/32, not quarter 20s. And these screws attach to the motor. So what we want to do is go back here and add two circles for these screws over here. Now I could add two more circles over here, but I'll show you guys how to use the mirror function in sketches using this. So we'll make these two equal, and equal. And then remember, I said we're going to use 10/32 screws, and so we can head over to this chart, the tapping clearance drill size chart. Again, there will be a link to this given to you. And so if you scroll down the screws to 10/32, and over here, as you can see in the gearbox, the screws are not like threaded in place. They should be able to slide in and out freely. So what we want here is a close fit, right? We never use free fit, and we only use tap if there needs to be a thread inside the metal. So for close fit and for 10/32, our diameter is 0.196. So we'll go over here in our sketch, we'll add a dimension for 0.196. There we go. Right, so how far apart are these holes? Where are they located? If we again move our motor, and if we measure it, so I'll go into tools, measure, and if you measure these holes, they are 2 inches apart. Now you could apply screws here and over here, but the problem in applying screws so close to each other is this motor is able to sort of fall backwards. And for the best stability, you want to have screws on the opposite ends. So as you can see here, this screw over here is on the opposite end of that screw relative to the center of the motor. So we'll do 2 inches. So we'll make these vertical first, right? And then we want them to be on the center of the motor. And then we'll make them 2 inches apart from each other. So 2 inches. Now they're going off the motor, so we have to make them centered. So what we could do here is add another dimension and make this 1 inch over here, because it's 2 divided by 2, so 1 inch. Right, so we want to have these same exact 2 holes on the other side. How can we just copy it over? What you can do is you can make a line in the middle like that, and what you do next is you hit mirror, and you can click these 2 circles, which will be the holes for mounting the motor, and then you select the mirror line, this middle line over here, and you hit apply, and now we have those same 2 holes over on the other side. And what you can do is, once you're done, you can make this line construction so it's not in your face and annoying you. Right, so we have our motors, we have our gears. What else do we need? So now the other thing about gearboxes is there's these motor holes for mounting the motors, and the other set of holes we have is for these screws over here, as you can see here. And these screws are responsible for holding this whole gearbox together. So remember, we have this first plate and then we have a second plate. And the job of these 2 plates is to keep everything inside and prevent it from like falling outside, right? And so we need to have holes for 4 more screws, because there's 2 on the top and there are 2 on the bottom, right? And these screws generally we tend to use 1/4-20s because they need to be strong and they need to last for a while, because this is the gearbox, and if there are problems in your gearbox, it's generally a bad thing, because if your robot can't drive, you can't do anything else on the field with it. So we're going to go back in here and we're going to add, we could add 4 new circles, or we could just do 2 and we can mirror those over. So we'll add 2 here arbitrarily and we'll make them equal, right, and the dimension for them. So if we go to our tap and drill size chart, again we're using 1/4-20s this time, and we want them to be able to go in and out freely, right? Because if you look here, they're not screwed into that side, they're screwed into the second plate. So for the second plate we'll have to use the tap dimension, but for the first one they have to go in and out freely, so we have to use the close fit, which for 1/4-20s is 0.257. So we can go in here and we can dimension them to be 0.257. There we go. And then what we could do is try to figure out where we're going to place them. Right, so again, we can make them vertical, but that would end up taking a lot of space, right? So instead of making them vertical, we'll place them somewhere over here. Now, another thing to note is if I were to just extrude this dimension for the hole here, right, I wouldn't have all this extra material around it. And you want to have extra material so that you can support it, right? And so what we need is a bit of extra material. And the way we can add that in our sketch is we can make another circle on top of our 1/4-20 hole. Same here. We'll make these 2 circles equal to each other. And you can give it a dimension of 0.5 inches. So what this means is if I cut out this hole that's 0.257, I will have guaranteed this extra bit of material over here. And that will make sure that my part is usable and I can put a screw inside it and not have it just fly off, because you need the extra material. Right, so I have my screws and I have my extra material there. And the reason why we need to do that for the motor mounting holes is because we already made the circle for the motor, and that provides extra material over here. Right, so where do we place them? Now we want our gearbox to be as compact as possible, right, because then it won't take up as much space. So what we could do is make tangent the circle here to the motor. Same thing over here, right? And so we're almost done placing these. Now how far in or out do they go? So remember, these circles over here are the actual gears. This gear and that gear. And if you look on our gearbox, these screws and the standoff comes really close to this gear over here, but it doesn't collide. So how do we make sure that we can get close so that it's compact but we don't collide with it? Well, again, remember how we use the outer diameter of this small gear to determine this size? We can do the same thing here. So if you go back to our drawings here, as you can see, the outer diameter of the gear is how big the gear is. And so we're using 44 and 42 gears. So if we look for 40 and 44, their outer diameters are 2.1 and 2.3. So what we can do here is offset these two circles, right? Because remember, the gears have to mesh with each other, so that's why the pitch diameter is smaller than the actual big diameter of the gear itself. And so we have these two offsets, and what we can do is give them dimensions. So this one was 2.3, 2.3, and we can make this one 2.1 because that's what it was, right? And so what this means here is this is this bit of overlap here. This is where the teeth of my gear mesh with each other, and this is the very outside of my gear. But obviously, if this is the outside of my gear and my standoffs are touching it, then that doesn't work because that would result in a collision. So generally what we do is we take this 2.3 and you can add an extra 0.1 inches to it. So that way we know that if the standoff is touching this 2.4, it won't actually be touching our gear, right? So that hole is done, and then we want to do the second one. So again, make this bigger by 0.1 inches, and now we can make it tangent to our standoff and our screw. So we have that here. Now all we need to do is mirror over our screw hole and the extra space around it using this middle line, hit apply, and there's our second set of screw holes. Now this 0.5 inch diameter circle here, that's also the diameter of the standoffs. So that's why I'm making them tangent, and I can be rest assured that I won't actually hit the gears because this 2.2 is bigger than my actual gear. Right, so now this is starting to look like a gearbox. The final step here is to connect all these, all these circles here with lines so that we have an outer shape. So what we do is we hit line and we can connect these two circles. We can come down here, connect these two, and we can connect these two over here. Right, as you can see, those connections don't look very good right now. So what you want to do is you do tangent and make these lines tangent to the circles so that you have a very smooth flowing shape for your gearbox plate. So we'll do that, and we'll do the same thing here on the top like that. And what we can do is we can mirror all these lines over. So once you make one side, you just do the other side. Hit that line and hit this line, mirror over our central line, hit apply, and there are the other set of lines. And we're only missing this one set on top, so we can just do another line in between those two circles, make it tangent, and there's our gearbox shape. Right, so what do we do now? Well, we can extrude it. So we can finish the sketch. Now you could save this as a separate layout sketch if you wanted to, but I generally make it and just extrude it. And so what we can do is make it symmetric, and for the thickness of this plate we generally use 1/4 inch aluminum because it's super strong and super reliable. It is heavy, which is why you don't see it everywhere on the robot, but because this is a drivetrain and we need it to be really strong, we can use 1/4 inch aluminum. So now what do we select here? Because we have a lot of things to select. So remember that these circles here are holes for screws, so we don't want to select them. But we want to select everything that's around them. So we'll just select these things here. And again, this is a hole for the standoff screws. So we'll leave that one out and we'll select everything else around it. And so we can just do that as we go around. And remember, these big holes here are for the bearings. So we want to leave those as well. But we can select everything that's around them. So you just work your way around, selecting everything that's not supposed to be a hole for something. and we're starting to get our shape here. And you might have these like tiny zones that you have to select, but you can just zoom in and select them. Select that, select this, and we are almost done selecting. There we go. There's our whole plate. We can hit OK. And so as you can see, that's our first gearbox plate. And we can attach our motors and screws and everything to it in an assembly, and we can make a whole gearbox. Thanks for watching. And we have to set up materials here as well, so don't forget about that. So we'll go back to aluminum 6061. I'll change the colors, and we'll save this as our gearbox. So now, thanks for watching.